So meaning is that in nav rendering, what I'll do is that for every pixel of the screen that I want, I will be I will be testing every Gaussian, to render one pixel, I will be testing 1 million Gaussians. Then to render the second pixel, 1 million Gaussian. So it is like highly inefficient. It is far too slow and compute intensive. So nav rendering I cannot do. I cannot test every Gaussian for every pixel. So that's why I have to bring some parallel computing into picture, and some innovation in the strategy. And that is what is tile based strategy is about. In tile based strategy, what I am doing is that I am breaking the scene into tiles. So instead of processing per pixel, we divide screen into tiles. Typical tile size is 16 into 16 pixels. So I will break it into tiles. So 16 cross 16. So 256 pixels at a time I'll have like this. Now the advantage I get with this method is that local memory, because these tiles I can process it in local memory. No special memory is needed because GPU shared memory very easily. These tiles, because 256 only pixels, so these tiles I can process it using local memory. Parallelization. This is very important because all these tiles I can render parallelly. Tiles are processed independently, and that makes it very fast and reduced work. Because of this tile methods, now every tile will only consider those 3D Gaussians which will fall on it. So we will skip irrelevant Gaussians. So that's a very big thing, because it's not like every Gaussian will occupy every tile. It will never happen because every Gaussian will have a position, size, shape, and orientation. So it might occupy 2 or 3 tiles. Let us suppose I have like a very big Gaussian, something like that. So it is occupying like 4 tiles at a time, max, or 5 tiles also. But it cannot occupy all the tiles. So we are skipping irrelevant Gaussians while processing a particular tile. And that's a very big computational advantage we get in the tile-based strategy.